Welcome, everyone. Today, we're diving into the critical role of high-performance polymer materials in lithium-ion batteries. As we move toward a more electrified future, the chemistry of polymers is proving to be the silent engine behind safer and more efficient energy storage. In this graduate seminar, we will explore their current applications, the technical hurdles we face, and the exciting developments on the horizon. To understand why polymers are so vital, we first need to look at the broader context. Our transition to electric vehicles and large-scale grid storage is hitting a wall with conventional liquid electrolytes and polyolefin separators. These traditional materials reach their limits in terms of energy density and safety. Polymers, however, offer a threefold advantage. They allow for thinner, lighter cell designs to increase energy density. They can eliminate flammable liquids to ensure safety, and their ease of processing through solution methods can significantly drive down manufacturing costs. Before we look at the new materials, let's refresh our understanding of standard battery architecture. In a typical lithium-ion cell, lithium ions shuttle between a graphite anode and a metal oxide cathode through an electrolyte. Crucially, a microporous polymer separator keeps these electrodes from touching while letting the ions pass. Essentially, the polymer components are the gatekeepers of the battery, governing how fast ions move, how stable the cell remains under heat, and whether it stays safe during operation. Let's focus on the first major component, the separator. Currently, these are microporous membranes made of polyethylene or polypropylene. Think of them as high-tech filters that are only 10 to 25 micrometers thick. Their job is a balancing act. They need enough porosity, around 40 to 60%, to let ions flow, but they must also provide a thermal shutdown feature. If the battery overheats, these polymers melt to close the pores and stop the reaction, acting as a built-in safety fuse. Moving beyond simple separators, we have polymer electrolytes, which come in three main flavors. First are solid polymer electrolytes, or SPEs, where the polymer itself, often PO, moves the ions. Then there are gel polymer electrolytes, which are like a sponge-like polymer matrix soaked in liquid, giving us the best of both worlds, mechanical strength and high conductivity. Finally, we are seeing the rise of single-ion conductors, where we tether the anions to the polymer backbone to ensure only the lithium ions move, which drastically reduces power loss and charging issues. The ultimate goal in battery design is the solid-state battery. By replacing all liquid components with solid polymers, we can fundamentally eliminate the risk of fire or thermal runaway. However, this isn't easy. To make these commercially viable, we need to solve the interfacial resistance problem, essentially ensuring the solid battery parts touch each other perfectly, while reaching a target conductivity at room temperature that matches what liquids can do today. How do we overcome these performance gaps? One of the most promising innovations is the use of nanocomposites. By mixing in ceramic nanoparticles like LLZO or alumina, we can disrupt the polymer's crystalline structure. This creates more amorphous or flexible pathways for lithium ions to speed through. Furthermore, these nanoparticles act like a physical shield, making the material strong enough to block dendrites, those tiny needle-like lithium crystals that can grow and short-circuit a battery. These material breakthroughs have massive real-world implications, particularly for the targets set by the Department of Energy and the EU's Battery 2030 Plus initiative. To meet the demands of the next generation of electric vehicles, we are aiming for energy densities of 500 watt-hours per kilogram, a service life of over 1,000 cycles, and the ability to operate reliably in freezing temperatures. Achieving these benchmarks is only possible if we innovate at the molecular level with polymers. Despite our progress, we must be realistic about the challenges. Currently, many solid polymer electrolytes only work well when heated, and common polymers like PEO tend to break down or oxidize when used with the high-voltage cathodes we need for long-range EVs. Additionally, as batteries charge and discharge, the solid parts can lose contact with each other, leading to high resistance. Overcoming these mechanical and electrochemical hurdles is the primary focus of current research. Looking forward, the field is moving toward highly engineered solutions. We are seeing the rise of AI-guided polymer design to discover new molecules faster and block copolymer architectures that create dedicated highways for ion transport. To summarize, polymers are no longer just support materials or simple plastic wraps. They're the enabling platform for the next generation of safe, high-performance energy storage. Thank you for your attention.